All right, welcome everyone. Yesterday we spoke about PyTorch, getting our entire environment set up, and how to get Jupyter notebooks to align to the correct kernel. Well, now that we did all that work, learned how to work with tensors, so then we're going to actually start working with how to build our models, right? We're going to build our very first deep learning model today. And we're going to start off with something called a binary model or binary classification models. We'll be talking by doing a small overview over the neural network. We'll go over the different types of layers that fall inside of the neural network. We'll then build this model utilizing nn from PyTorch. And then we'll talk a little bit about weights and biases, how they're applied at each independent level. We're not going to go too in depth into all the math because it gets a little complicated, and I'm definitely not a math magician either, so I'm probably not going to be the correct person to be going in depth into how those things are calculated or how they're implemented. And then finally, we'll be going into how to create our learning model rather than a regular sequential stack into an actual Python class for a learning model. All right. At this point, does anyone have any questions over what we'll be covering during part one of our lecture today? Let's hear it, Gary.
Is this one you recommend following along with you or just taking notes?
I'm going to go ahead and say that it's off the bat, it's up to you. I strongly recommend that you do not follow along with code because if you run into an error, um, it causes a little bit of an issue, and then people feel like they will have to fix their code and continue following along. Um, and if you do decide to follow along, as soon as you crash into an error or if you do interact some sort of obstacle, just stop following along. Pay attention to the lesson and prioritize just retaining the material that I'm going to be covering. Does that answer your question, Gary?
It does, thank you.
All right, fantastic. Well, let's start off here. Well, as I mentioned, we're going to be building our binary model here. But what does our binary model actually look like, right? Well, here I have a small example. We'll also see it inside of our curriculum of what a binary model may or may not look like. In this case, what we have here is a neural network, fully connected, where we are going to accept 3 separate neurons at a time. Those neurons will go through a hidden layer process where they will fall into 2 neurons, and then finally into 1 output neuron. That 1 output neuron, before becoming our actual output, will go through an activation layer, and then we'll provide our output. Now, we're getting a little bit of an image here as to a better example of what inputs may look like and what our output may be. Specifically in binary classification models, what we're going to be looking for here is going to be where our output is anywhere between 0 and 1. And what we as developers will do is run an if statement checking, hey, if this number or this output is closer to 0, then this is false. And if it's closer to 1, then it is true, right? We're never going to get a well, excuse me, shouldn't say never. It is very unlikely that we will get a definitive 0 or a definitive 1. Those would be really amazing cases. We all need to realize that all our model is essentially going to be doing is taking random guesses and then utilizing our training to get either an affirmation saying, hey, this guess was correct. Whatever logic you utilize to make this guess, maintain that logic. Or us telling it, this guess was completely off. Whatever logic you did, you need to adjust it. This is the correct answer. All right. And I see there's a question. Go ahead, Lynn.
So I'm assuming we're going to go over like different classification models, and the binary is the first one. Is there like an example, like a real world example of where this would be used? Because I understand the ones and zeros, but I'm just, if I was really developing this in a system, what is like the standard example that gets whipped out all the time for binary classification model usage?
Yeah, as far as usage goes, I'm not sure if you're asking for a specific example as far as like what it would look like inside of an application. If you're asking as to its usage, binary classification models are just true and false, right? And they're used in multiple ways. I had a couple of examples here in the curriculum. Oh, there you go. So one of them is email spam detection, right? We get an email. Sometimes my email says, hey, this is spam, straight off the bat. It doesn't even fall into my regular inbox. Rather than falling to my regular inbox, it goes into my spam. Well, how does that happen? Well, likely whatever email service it is that I'm trying to utilize has some sort of learning model in the background that every time an email is sent to my inbox, well, it gets fed through that learning model. That learning model looks for specific keywords, or it's been trained to be able to identify what a spam email structure would look like. So it would go through it, identify, hey, this is in fact a spam, and then change that Boolean variable in the database. And then rather than seeing it in my regular inbox, it would fall inside of my spam.
Okay, that makes sense. Because it's like, is it poorly spelled? Is it a batch email? Does it come from an own address? Those are like and if it has enough of these key things, it flags it true. And if not, okay, that makes perfect. Thank you for that example. Thank you. That's exactly what I was asking for.
Of course, no problem. Any other questions? All right. If there aren't any other questions, let's go ahead and actually start building this information so that we could see what our model would look like at each independent layer. All right. Well, I already have my binary tools here, or my PyTorch working. I'm able to print out my version. I'm just going to open up some Markdown here. And I'm going to talk about how to build a binary model. Now, for building a binary model, we're going to need a series of tools from PyTorch, right? Yesterday, we learned all about the tensor, which is great. And it's going to help us with data manipulation before we actually start training our model, or feeding data into our model. As we know, all of our data is going to be represented as tensors. Well, how do I actually build my model? Let's take it one step at a time. All these linear layers, or hidden layers, excuse me, they're typically just a representation of something called a linear layer. All right. So this is going to be coming in from PyTorch, and I'll be talking about where it comes in from. But a linear layer is, its main purpose is to receive a number of neurons, and depending on weights and biases, output a set number of neurons. So let's go back to our example here. What is actually happening at each level of these neuron codes, right? Go ahead and highlight here. Try to open it up a little bit to give us a little bit more real estate. And I'm going to make these quite a bit smaller. Well, at a hidden level, right, we don't see it, but this is actually a linear layer. All right, we have our linear layer there. Well, this linear layer specifically is designed to receive three three neurons, right? And it is also designed to output two neurons. All right, our next linear layer on the right-hand side, and let me go ahead and move this over a little bit. our next linear layer on the right-hand side is built to receive 2 neurons and output. Yeah, it might be easier if I just do this, so I don't have to mess around. 1 neuron, right? So there we can see, hey, 2 neurons are being passed over directly into the next linear layer. That linear layer is then outputting a 1 single neuron. And then finally, our activation layer, well, depending on which activation layer we choose, which we'll be talking about activation layers here shortly, it is designed to grab the output of the last linear layer or the layer right before it, whether it's a linear or an activation layer, because sometimes we could have some that are sequenced. And let me make that medium here and change its color. All right, there you go. And mutate or flatten this information to ensure that it matches the format that we want. So in this case, if our linear layer's last output is, hey, well, this output's still somewhere around 3.57, some crazy number, right? It's nowhere between 0 and 1. Well, my activation function, because I'm trying to achieve an output between 0 and 1, well, my activation function needs to be something that will grab that output and run some form of calculation to make that output in between 0 and 1. Now that I've said that out loud, and I think about the different types of activation functions that are available, in binary classification models, your activation function will, the majority of the time, if not all the time, be the sigmoid function. And the sigmoid function, oh, let me change that color. The sigmoid function, what it does is it runs a little bit of math where it essentially takes in the last element and it squeezes it or flattens it to fall between 0 and 1. Again, I'm not going to talk about the underlying math of what's going on here because that math can get pretty complex. So we're going to keep it at the top layer there, where the sigmoid function will take the last input and ensure that it applies between 0 and 1. And at this point, my sigmoid function, or my activation layer, does not have weights and biases anymore. All right, it just takes the output. Because this is my output, I'm just mutating it or running an activation function to ensure that it follows the correct format that I need. All right. So there you go. These are going to be my tools that I need. I need my linear layers, and I need my sigmoid activation. So I need sigmoid in order to ensure my output is within the range of greater than or equal to 0 and less than or equal to 1. All right. Does anyone have any questions about this information? What our linear layers are doing, how they're accepting information and outputting information, and then what our activation layer is going to be doing for us here. All right, great. Well, doesn't seem like there are any questions. So let's go ahead and move on to the next portion here. Oh, we do have a question. Go ahead, Brandon.
So from linear layer to linear layer, so through the first layer, are those, you said those are predetermined what it passes to the second linear layer, or is it based off of whatever calculation that layer runs?
So you actually dictate how many neurons you'll be passing in between here. So when you create this linear layer, which we'll see here shortly, you'll specify the number of inputs that that linear layer should be expecting, and you'll specify the number of outputs that that linear layer should be passing on to the next layer. And then they should just
Okay,
change.
so it is predetermined.
Correct.
Okay, thank you.
Of course. All right. So now, finally, yeah, we talked about how I build these layers or how these things come into play. But as we've seen before, even though I have these layers all laid out, I need some sort of holder, right? Or something to actually encompass this entire thing and hold it together to ensure that it actually, as data goes into the model, it gets compiled in a sequential manner from left to right from each individual layer to achieve my output. Well, in order to do that, this all gets wrapped, and maybe I should utilize a box here within a, let's see what color. Nope, that doesn't work. That doesn't work either. All right, there you go. This all gets wrapped within a sequential model, right? So the sequential will ensure, or the sequential is actually just a tool that comes in from PyTorch that allows us to build this hidden layer functionality without us manually having to pass it from one layer to the next, right? Which we'll take a look at how to do it manually. And then after we see how it's done manually, we'll go into how to do it with sequential. So that's our final tool here, which is sequential, which is utilized to easily define a model and a number of layers and steps within our model. All right, great. So there's my information. I have what I need to be able to start building my model. Let's start by doing some imports here. I'm gonna open up another code block. And what I'm going to be importing here is going to be the nn portion of PyTorch. I'm going to say from, or excuse me, it should be from torch import nn. And I'm going to say that I want to reference that as nn moving forward. You could simplify this and just do capital N. You could give it some sort of other alias if you don't want to just do nn. This is all just setting an alias. Right? And then finally, I'm going to go ahead and say, well, nn will give me the ability to utilize my linear, sigmoid, and sequential. So let's go ahead and write that. Let's say linear 1 is equal to nn.linear. And as we saw before, we can specify the number of inputs in output neurons. So in this case, I want an input neuron of 3 with outputs of 2. My second linear layer should have outputs of 2, or excuse me, an input of 1 and an input of 2 and an output of 1. And then finally, we have my activation layer, which will be nn.Sigmoid. Right, and sigmoid, I'm not going to specify anything because it already has its pre-built functionality. It's only expecting 1 neuron. All right, great. If I run this, we'll see that it all runs properly. It didn't raise an error. So let's go ahead and put this to the test, right? Let's actually start writing or feeding a tensor to this information. Gonna go ahead and bring in this tensor straight from demos and notes. You'll notice that these are all float numbers, and we do have, in fact, 3 neurons, right? When I try to feed this to linear layer 1, all I would say is output of ln1 is equal to linear layer 1. Oh, and I should probably call this an input tensor. And I'm going to pass the input tensor. And let's go ahead and print the output of ln1. All right, so there we go. We fed 3 neurons in there, all of them with the number of 1s. We fed it into our linear layer 1. We defined it. We pass an input tensor. And when we print the output, you can see that the output is now a linear layer of 2. All right? Or excuse me, a tensor of 2. So I received 3 neurons and outputted a tensor of 2 neurons. Well, let's go ahead and take a look at what this will look like when I then feed it through my second. So I'm going to say output of linear layer 2. And what do we think we're going to feed it here? Right? I'm going to go ahead and call linear 2. But what will be fed into linear 2? Can anybody take a educated guess at this point? Let's hear it, Eric.
It'd be the output of linear 1.
Yeah. I would feed it the output of linear 1, right? Because if I try to feed it my input tensor, well, my input tensor is of 3 neurons, so it doesn't match the required input. I already mutated my input tensor to be a tensor of 2, and now I'm changing it to be a tensor of 1. And I forgot to change this to the number 2 here. And now we have 1 tensor. Well, finally, we would feed the output of 2 yeah, let's just call it result to my activation function. And that will be my model's last guess, right? This is my actual model making some sort of prediction as to whether this is true or false for this tensor. So now I feed it through. It went through the sigmoid function, my activation function, and this is what it returned. It returned 0.46, which is less than 0.5. So it tells me that my initial input tensor would be classified as false. All right. So this is how you start your neural network, or these are how the tools of the neural network would work if I was calling each one of them independently. Right now, I'm manually forcing these connections by passing each one of these arguments from one to the next. But there's got to be a more efficient way of doing this, right? Of doing this forward pass of data from one linear layer to the next. Well, the easier way of doing this is by establishing a model. Rather than writing each one of these, the passing of the forward pass of this data from one layer to the other, I can rely on Sequential to do this for me. I can call nn.Sequential, and I can just specify, hey, I want a linear layer of 3 neurons with an output of 2. I then need a secondary linear layer of 2 neurons with the output of 1. And then finally, my activation function will be the sigmoid function. right? And that will conduct the same behavior. Well, this will save my model. And I can then say, well, I want the result to be of my model that is taking my input tensor and feeding that input tensor sequentially through the neural network. All right, we still have our print statement down below. Let me go ahead and bring that back. Well, when I run this, we can see that it came out with a separate guess, but it was effectively feeding our data through the neural network. All right, we passed in our input tensor, where it received the first 3 neurons, turned it into 2, passed it to the secondary layer, grabbed the 2 neurons, turned it into 1, and then passed it through our activation function to ensure that it's making a consistent prediction between 0 and 1. All right. And just like that, we just built our first learning model. Does anyone have any questions over building your first learning model for binary classification? Let's hear it, Cody.
So is that basically saying input of 111 has that whatever percentage came out chance of being inside of this model, of fitting in this model? Is that what we're doing right now?
Currently what I'm doing is I'm evaluating if the data, let me see if I could think of a better example here. So let's say we're trying to determine if a social media comment is offensive or not, right? Well, I can't evaluate text, or a machine can't evaluate text per se, right? We know that machines work off of numbers, and that's how we're able to run quick and easy computations. Well, let's say this text is only of 3 words, right? Those 3 words would get turned into numerical values, right? And this model would then be evaluate if comment is offensive. We'll just say that, right? Well, these 3 words are turned into a numerical value, each word corresponding to 1 number. It gets fed through the neural network, and we trained this model to identify whether a comment is offensive or not. All right, so this may turn into something where rather than specifying, hey, this is 3, we may have some sort of function that makes us a little bit more dynamic for the initial state, right? But then everything else stays the same. Well, now it grabs that comment, feeds it through the neural network, and what we wanted to evaluate is, hey, if it is offensive, this output tensor would be greater than 5. So in this case, what we have is 0.569. So it tells me this is an offensive comment, where if it was less than 5, then it would not be offensive. It's evaluating true or false. Does that make sense, Cody?
It does, yeah. So the function we're setting it through has already been trained. So that model's been trained by us already, and now we're evaluating. So, okay, yeah, that does. Thank you.
Of course. Yeah, in this case, we have not trained the model. This comes with already built in weights and biases that essentially, when we build this and we call the linear layer will randomize some weights and biases to get us started. And then through the training process, those weights and biases will change to ensure that the model is actually making accurate predictions. All right, Brandon?
Where are we actually converting this data? So like right now we're just using random numbers.
Yes, that's correct. Right now we're utilizing random numbers. The data conversion is going to happen during part 2 of our lecture.
Okay.
All right. Okay, so now that we've built our model and we were able to feed some tensors through, or a tensor through it, let's talk about what are acceptable tensors and what are not, right? Because so far, and actually I probably don't want to delete that. Let me go ahead and, yeah, just in a separate code block, we'll go ahead and talk about acceptable and not acceptable tensors, right? So currently, my neural network is expecting to have a initial value of 3. So if I had a tensor that looked like this, right? So if my tensor looked like this, and oh, that is not what I wanted to do. Let me add some code here. There you go. Now, this tensor is a 1, 2, 3, 4, 5. It is a 3 by 5, right? Tensor. All right, if I were to check the size, it would be a 3 by 5. Now, would this be an acceptable tensor to be fed into my neural network? What do we think? Both yes or no are good answers here. But let's hear it, Brandon.
I'm assuming no, but if you can feed each row in, then yes. But if you're just feeding the whole thing, then no, because it has 5.
Yeah, it's a great that's good. That's a great observation, right? Well, each one of these sublists, we could actually feed this into our model. And we could do that because each list is of length of 3, right? So it expects the neurons, which is the representation of each individual number within the subtensor, to be a total length of 3. So as long as each sublist has the length of 3, it could be fed through our neural network. But what would that look like as far as output? Let's go ahead and change this to be our input tensor. And let's make our output here and make that equal to our model that expects our input tensor. Let's just print our output. Well, when I execute this, you'll notice that I had 5 separate tensors of 3 or 5 separate lists of 3 neurons. Well, it returned to me 5 separate predictions, right? It went through each level, analyzed that there was 3 neurons, and it returned a prediction for each one of them. So for this first tensor, it evaluated to true. And for the remaining 4, it evaluated to false because it's less than 0.5. Right? So it's able to take in as many rows as you want. What it cares about is the number of neurons within each list. Right? So if I were to switch up my tensor and try to feed it something like this, where I have 3 rows, but I have 4 neurons instead of 3, when I try to execute this, it's telling me, hey, this doesn't work. You're trying to feed 4 specific neurons into this, all right? And here it tells me mat1 and mat2 shapes cannot be multiplied because I have a 3 by 4, and what this is expecting is just a simple 3, right? It wants that 3 to be inputted so that it can put out 2. All right. And I see we have a question. Go ahead, Eric.
So I have a question the way the model works as we currently have it defined, because we've talked about like the back propagation feedback of like the weights changing every time you pass more data through it. Was our most recent output affected at all by the first inputs we ran through, or is that not really, is the feedback built in yet, I guess is the question.
Yeah, that's a great question. So the term that Eric just utilized, which is called backpropagation, is in reference to telling the model, hey, this was not a good answer. I need you to go back through the model, each layer at a time, identify backwards how you came up with this answer and how you could change it so that the answer is correct. And then all of these these weights and biases would adjust in a backwards motion, right? So I would get the output. I would say, hey, nope, this is wrong. I need you to fix yourself. And it would start fixing itself from the back or the end of the model all the way back to the start of the model. Wow, there you go. Go ahead and make that extra large, and let's turn that back into solid. All right, and that is something called back propagation. As of right now, to address your question, Eric, we're just making predictions. Our predictions do not affect the next one because we're currently not within the training iteration of our loop. We're not implementing the back propagation step. We are only implementing the forward pass of feeding data through the neural network. Does that answer your question, Eric?
Yep, thanks.
Of course. Dustin?
Is this like having to do with quantization? Like 2-bit, 4-bit, 6-bit, and how accurate it is? Or 2, 4, 8?
What do you mean by this? Are you referencing to back propagation or are you referencing to Go ahead.
Sorry, not back propagation. The how many layers we're adding in and how, right? So how much we're putting in there and how much it's evaluating each one to the next one.
Yeah, I would think of it as that's what's going on under the hood, right? It's expecting a certain number of inputs in order to actually be able to compute and run the mathematical operations that it needs to do and be accurate. So it tells me off the bat, hey, you're not giving me the correct information. I can't work with this because I can't give you a good prediction, right? To go off of that, if I were to try to feed it a tensor to my model that looked like this would also fail. All right, if I try to execute it, it tells me it fails. Well, why does that fail? I have a 1/3 tensor, right, where I have 3 specific elements here, or 3 neurons. I don't understand why that would fail. Well, if I scroll down through the error here, oh, excuse me. If I scroll down through the error here and I come all the way to the bottom, it tells me, hey, mat1 and mat2 must have the same data type, but long and float, but got long and float. Well, these integers or solid integers are being interpreted as long, right? That's what that's being referenced to. But everything within our neural network, as far as weights and biases go, they're interpreted as floats. So when this neuron or when this tensor gets fed into my neural network, it tries to multiply this long interpretation of a solid number of 1 or conduct mathematical operations to this solid number of 1 times a floating number or a floating number of tensors. Well, it can't do that, right? Or at least it can't do that accurately. So it very much straight off the bat tells me, I can't do this. It's not going to work. You need to ensure that this is a float that you are feeding in order for me to work correctly. Luckily, data may not always be in floats. Sometimes we may receive data that is being interpreted in solid integers. So in order to feed it to our neural network, all we need to do is type in input tensor dot float. And then I'm going to go ahead and print out our input tensor here so we could also visualize it. So it took the original input tensor and it just added it just casted it, data casted it into a float so that our model can actually accept the tensor and make a prediction. Does that answer your question, Dustin?
Somewhat. Yeah, I mean, it seems like we're determining how accurate it is, right?
No, we're not determining how accurate it is yet. Right now, we're just feeding tensors through it. We built a network, but we are nowhere in the process of actually fixing its predictions yet.
Or I guess maybe maybe not accurate is the right word, but like, would you add more linear layers, like so you can have more inputs, or like, I guess, what is this determining?
Yeah, that's a great question. So currently right now, my end goal, right, was to, one, I was able to identify the number of features that I had here, right, which was 3. And I decided, well, since this is going to be a binary function, I need to ensure that by the end of this model, I only have 1 at the very end. I could have made this a 2-layer model where I just had 1 linear layer that accepted 3 and spat out 1 neuron and then done my activation layer. But I typically like to do the whole 3/4 rule where I cut it down slowly. So in this case, I did 3 to 2, 2 to 1, and then finally my activation layer, right? As far as deciding how many linear layers you need, we'll be covering that later on once we go into training our data. Did that address your question better, Dustin?
Yeah, got it. Thank you.
Got it. All right. So now we were able to talk about what is a valid tensor. We were able to go into a little bit of our tensor methods that we learned yesterday to be able to cast a tensor and effectively feed it into our model. So now that we've talked about that, let's talk about weights and biases, right? Because as of right now, I can see a lot of questions are being raised as to, well, how is it actually making these predictions, or how are we training it or trying to tell it where these predictions are happening? Well, we can access each individual layer of weights and biases within the model. So here we go. Let's do weights and biases. And we can access each layer within the model. And I should say each layer's parameters within the model, right? So that's all weights and biases actually are. They're just parameters. They're things that are utilized to ensure that we're receiving accurate information here. So let's talk about this. I'm gonna go ahead and open up my code block. Well, I'm gonna show us how to access each level of the model. So at model index 0, what I have is my initial linear layer that took in an input of 3 and an output of 2. All right, if I execute this information and say, hey, I'm a linear layer, the input features that I'm allowed to receive is 3, and the output features that I will put out to the next layer is of 2. And I do have biases being involved. Great. Well, that's fantastic, but I want to actually see what your biases look like. All right. Well, I can do that by just adding the dot biases. And I think it's bias in this case. Let me make sure. It is. And once I run this, I get, hey, this is a parameter that is containing the following information. Now notice it's containing a tensor of a 2 dimensions, right? Well, it is accepting 3 neurons, right? But it is only outputting 2 neurons. So typically biases have to deal with the output portion of our linear layer. And then here comes our weights. Well, our weight, we received 3 neurons, and we're placing out 2. But notice that we have 2 tensors that have 3 neurons. All right. Well, we are accepting 3 neurons. So I need to be able to affect each one of those neurons by an index, and that's where we get this 1 by 3, right? But I am creating 2 neurons. Because I am creating these 2 neurons, I need 2 separate weights to be applied. One that will be applied to these 3 neurons, and create this next one here. And my second tensor down there, or my second list down there, that will still be applied to these 3 neurons, and then create the second neuron down there. All right. So weights are in reference as to how we change the data from one to the next, and biases have to deal more with the output layer. Does anyone have any questions about that or how to view them? Let's hear it, Daniel.
I guess so. My question is, so I see for the tensor we have 1 point, comma, 1 point, comma, 1 point, comma. How, I guess, how are we getting this negative 0.3583 and the rest of the numbers? Like I thought it'd be like a fixed number, or I don't know how. I guess my question is, how is this interpreting the 1 point? Is it like a range that we're getting?
Yeah, got it. So linear layers come whenever you create a new linear layer, it's going to be created with its own weights and biases already. So this has nothing to do with our actual input tensor of 1111 or 1.0, 1.0, 1.0. This weight was created the moment I typed in nn.Linear 3 of 2. The moment that this gets executed, PyTorch grabs a random weight and a random set of biases to apply at each level. And it starts off with random stuff. Like I said before, it's like the method of as much stuff as I can throw at the wall, eventually something will stick, right? That's what PyTorch is doing here. It's generating a random amount of weights and biases, and then it's waiting for me to put it through the training process to actually fix these weights and biases so that they're accurate. Does that make sense, Daniel?
Got it. Thank you.
Of course. So created at, well, we saw that we can access a model at index 0, and this is going to be the first linear model, or excuse me, my first linear layer. I can also access the second linear layer by doing index 1. And there we can see that index 1 only has weights for 2, right? So there's 2 neurons in there. So it has 1 for each neuron, and it's only going to be creating 1 new neuron. So it's only a 1 by 2 dimensions. Whereas before we had 3 neurons and we were creating 2. And that's how we got a 2 by 3 dimension. All right, so there's our weights. Now, if you ever needed to see all of them or have them all listed out so that you could run some sort of operation on it, you could always utilize a for loop. You can say, and let me actually comment this stuff out. No, I'll just put in a separate code block, actually. You can specify for name and parameter in model.named parameters. And let me actually, before we see this for loop, let me show everybody what this function returns. So I have model.name parameters. Well, this returns a object of the class, right? Well, it returns an object of the class, but this is an iterable object that has specific tuples, right? So essentially what this looks like is as a list of 2 index tuples. So what we're going to do is we're going to destructure this information. I'm going to grab the name and the parameter in models or in model.named parameters. And what I'm going to do is I'm going to say, hey, if the parameter. And first, let's go ahead and just print out all of them. All right, let's say name and parameter. So there we can see the name and parameter. It goes through, it shows me the weight and bias of the first layer, and it's identified by, hey, this is the first layer, which is index 0. Here's the weight. This is the first bias, which is index 0, and here's the bias. All right, and then it goes into index 1, which is our second layer, and provides me both the biases and weights. And that's how I can view both of them. All right, let's hear it, Dustin.
Is this the same parameter that, like they say 7 billion, 13 billion? Is that similar parameters that this is talking about for models?
7 billion, 13 billion. I'm sorry. I'm gonna need a little bit more detail. Can you specify a little bit?
Well, it's just how they classify a lot of like LLMs, like 7 billion, 13 billion, like the weight or how much that it takes in, like 30 billion.
Got it.
We can look over that later. It's just same language.
No, that's a great question. I am honestly not too familiar with that topic that you just mentioned, so I'll make sure to look into it and get back to everybody with a good answer for that.
Yeah, no problem. Thanks.
Of course. All right. Oh, go ahead, Gary.
Just so I understand, so the weight and biases are going to be added to give more so like what is more pertinent for the data, and then what determines the weight and the bias? Like,
Okay, yeah, good question. So weights and biases, the moment you create the linear layer, the weights and biases are created already. They're just randomly created. The program knows that we're going to need weights and biases to start making some sort of estimation. So it provides us some random number, some random creation, right? It's not trying to run any crazy logics to ensure that it's going to accept some sort of number of a specific range for each neuron. It's not doing anything like that. It's literally just out of nowhere, it says, oh, well, you're going to need this stuff. I'm not sure which one specifically you're going to need, but I'll give you this, right? And it just gives me something random. Now, as to how they're being applied, let's go ahead and go into that. I'm actually going to go ahead and revert to our curriculum here and try to read it to everybody so that I don't go too far off the rails here. But so for example, our linear layer, right? My very first hidden layer. Yeah, my very first hidden layer. What it's going to do is it's going to take my input tensor, so what I'm feeding it through, which in this case, let's go ahead and grab that tensor. Yeah, there you go. All right, it's going to take this input tensor. And what it's going to do is it's going to then multiply this tensor. And we've talked about multiplication before, right? So here's my my weights. Let me grab it here. Maybe we could just see it in code. So here's input tensor. And this is going to be a tensor. Excuse me, torch.tensor of ones. All right. Nothing crazy here. Well, here's the weights on my first linear layer. And I can just grab this straight off the bat. Let's say first layer weights. All right, and I'm just going to take off that grad argument there. And try to format this a little bit so that we can see it. So it's going to take the input tensor in the first layer, right? And the very first thing it's going to try to do is it's going to try to multiply my input times the tensors that I have here, right? Or times the weights. So it's going to say, let's say weighted input now. And it takes my input tensor and multiplies times my first layer weights. And let's print my weighted input. All right, so you'll see that my input tensor is 1.1 or 111, right? And here is all of my layer weights. Well, doesn't really do me much good to do it this way. Let's go ahead and do some solid multiplication like this. All right. So it's going to run multiplication. We see here that we have 0.35. Well, it multiplies that times 2. It's doing element-wise multiplication times the 2 layers, right? When we talked about what this is called, oh man, we talked about it yesterday. I forgot the terminology off the top of my head, but essentially it's turning this 1 layer into a set of 2, right? This is what I fed it. We know it's expecting 3 neurons, and 2 are going to be outputted. Great. So there's my information so far. Well, now that I have this tensor as to with some weights applied into it, where does the bias comes in? Well, I'm going to say calculated input, and this is going to take in the weighted input and now add the bias, which if I go back and grab my bias, here it is. All right, so there's my bias, all right? And I would just add it to my first layer biases. So now let's go ahead and take a look at our calculated input as well. All right, this doesn't seem to be running the way I expected it to. I don't want to go through the whole process of debugging it here and trying to, in that process, confuse everybody even more or confuse everybody. So we have our input tensor. That input tensor gets fed to the neural network. That neural network will determine at random a different standard for weighted biases, or excuse me, for weights. It will apply those weights by multiplying it, and then it will try to compensate for the biases by adding the bias at each tensor level. I see a question here from Brandon Yo. Go ahead, Brandon.
Is the reason because you're supposed to be making the tensor into a dimension of 2, but instead you're just multiplying to every single element?
Yeah, so let's go ahead and try to do that. All right, let me bring it back here. So when I try to add it, it runs into a problem because I'm trying to add my weighted input, which, as you mentioned, if I print weighted input dot size and I comment this out, we can see that the size is 2 of 3, right? Where in the other one, if I do my first layer biases dot size and try to run this, you can see that we have 1 of 2. This could be to where I just need to nest it or unsqueeze it. So let me try to do that. Unsqueeze. And I think it's -1 in this case. Let me check. So if I turned it into -1 and then I do dot size. Two, three, and 1. Okay, so let me try to do it this way where I unsqueeze it. Yeah, it's just still running into some errors. There's some under the hood stuff that this is doing to ensure that this is compatible. I just gotta try to go back and ensure that I know how to replicate that in code. But essentially what it's doing is it's formatting the output of this multiplication so that I can successfully make the addition of the bias. Does that answer your question, Brandon?
Yes.
All right. All right. And it does that at each individual layer until it gets to the sigmoid function. And the sigmoid function, as we saw, that one's actually just a pretty simple one. It just grabs the information, takes it in, and ensures that it falls within 0 and 1. We have a pretty good breakdown of this in our curriculum. So maybe we could take a look at it in there here. All right, so here's our curriculum, right? And here it goes into talking about how it works. Oh, I might have skipped it. All right, so here's my first linear layer and how it works mathematically. All right, it takes the input tensor and multiplies it times the weight and then adds the bias in there. So here it shows me the input tensor is being multiplied times the weights. All right, so there are the weights of my first layer. After this multiplication is finished, it then adds our bias or biases to ensure that my first hidden layer output is created with 2 tensors, right? At the second level, it does the same thing. And then finally, the sigmoid function happens. And then there's a mathematical breakdown of how it works, right? So here's my hidden layer output at 0. So it takes my initial layer, it multiplies it times each individual tensor. So here we see 0.1 being multiplied by negative 0.4, 0.2 by negative 0.5, and 0.3 by negative 0.3. And then finally, my biases are being applied. Right, so here's the result of the multiplication. And then here's the result of applying the biases to each one of these addition and plus statements. Right, so there's the output of my first layer. And then here's the output of my secondary layer. All right, so here you go. Here's my hidden layer output 0, my hidden layer output 1. And I apologize, not first and secondary layer. These are the first and secondary neurons. All right. Then it goes into the second layer calculation, which does exactly the same thing as above, but just at the next level, and then puts it through the sigmoid function. All right, and that's how our weights and biases are being applied into the model so that we're consistently adjusting. We'll go into how to actually train our model, not in today's lesson, but in the one that we'll be covering on Monday. sometimes you may find yourself in a situation where you have to manually dictate the weights and biases for your code. It is not common practice, but this scenario does happen. If you ever find yourself in a situation where you have to do it, I'm going to show us the command here, but note that you're not really going to implement this very often. Right? Let's say that somehow my data got messed up, or my model got mixed up, or maybe one of my weights and biases is completely different than the remaining of them. Right? Well, I go through the process of grabbing all my weights and biases, calculating the means for all of them inside of a layer. And I want to fix the weights and biases for one layer to represent the mean of all the other ones. Well, I can utilize model, specify the layer that I want to grab the attribute of weight, and just use the equal sign to set it equal to something. At this point, you'll still utilize nn to call the parameter tool. And in here, you would just pass in the tensor that you want to apply, which in our case, we know that we need 2 weights. So I would pass in a torch tensor of a 2x3 tensor. Right, so there's my first one. And then I could apply my second one. I think I just broke this by putting a nested bracket there. Okay, good. And when I execute this should work, right? It would change the weight. Let me go ahead and demonstrate that it's actually changing our model weight. So at model 0 dot weight, and then model 0 dot weight. Oh, because it was already saved in memory, this had already happened. Let me go ahead and restart our kernel so that we have brand new memory, and let me execute all. All right. So there you go. We can see that our weights were originally this 0 point, whatever it is that our linear layer decided to come up with. And I then manually set the parameters for the weights myself. And when I printed it again at that layer, it shows what I passed into it of a tensor of dimensions 2x3, where all of the indexes are represented by 1.0. All right. At this point, does anyone have any questions over what we've covered so far? All right, I see there's a lot of good information going off on the chat. That's great. And thank you, Erica, for ensuring to put that inside of demos and notes. Oh, excuse me, demos and notes inside of the Whiskey X-ray channel. Okay, great. Well, we've covered quite a bit of information. We talked about how to make our neural network and how weights and biases are being applied, but this doesn't really follow our OP conventions as far as our model goes, right? So let's go ahead and turn our model into a class. So I'm going to scroll up here and steal our model so that we have it easily, so that we're able to see it easily down here. Now, utilizing sequential definitely works for our model, and it's been working so far. The problem with sequential is that, as you'll see in later on projects, it doesn't really have the capability to handle more dynamic or complex learning models. Or if we wanted to add some sort of step like skipping in case some sort of condition was met, Well, sequential doesn't know how to handle that, and it wouldn't be able to do that. So in order to break up sequential and specify our own manual method of conducting the forward pass, we can make our Python learning, our PyTorch learning model into a class module that will still have the same amount of linear layers, still have the correct activation function, but we ourselves will dictate the forward pass rather than letting sequential feed it right there. This is just to give us back the control. All right. So I'm going to start off by specifying, hey, this is going to be a class, and I'm going to call this my binary model. And this is going to inherit from nn.Module. All right. So I'm utilizing inheritance here. And this isn't some sort of object relational mapping like we've seen in Flask or like we'll see in Django. So I can't just inherit and not apply regular OOP rules, right? So if we go back in our time machine and go back to regular OOP, when I utilize inheritance or I create a class, what's the first method that I need to specify for this class? Let's hear it, Brandon.
Is it init?
Yeah, we need an initializer. So we're going to go ahead and create our init function here, or method, I apologize, which is going to be referencing to self. And just like before, we would run super dot init. All right. Now, just to make sure that we have the correct complexity, we're going to go ahead and take this super argument. And instead of just letting it run its default values, we're going to specify that we want it to conduct the super init function within the binary model and self. Right? So it's looking at the binary model, it's ensuring it's part of itself, and then going into the binary model to initialize the inherited class of nn.Module. All right. So there's our init method. I'm able to initialize information, but just like before, now I want to add some attributes or some layers into my learning model. So how do I create an attribute? All right, let's say I wanted to create an attribute of linear layer 1, linear layer 2, and then activation. Those are my 3 attributes that I want to create. And I want it to essentially resemble my model up above here. How could I do that? Can anybody walk me through the process of writing these attributes and setting them to a value? Let's hear it, Brandon.
Self dot underscore model is equal to nn.Sequential, and then pretty much just copy pasting everything else.
Yeah. So that's pretty close, right? This is something along the lines of what we want. But what we actually want to do is we want to take control back, and we don't want to utilize sequential anymore. So we're going to get rid of sequential. And we're going to get rid of this as well. So again, the attributes that I want to create are linear layer or linear 1, linear 2, and activation. So it looks like I already have the values for each one of those attributes. But how do I create these attributes?
So just self dot underscore linear 1, 2 in activation, and then
Yeah, so we'll go linear 1, self dot linear 2, and then self dot activation. right? And then they would just follow these conventions here. And it's probably going to be faster if I actually type it. All right, so just like that, we've built our model with the correct number of layers. Well, this is good. But Sequential was in charge of conducting the forward pass for us, of passing data from the left side of my model all the way to the activation function and providing an output. Well, now that we're not utilizing Sequential, I have to specify the forward pass myself. And you do that by creating a forward method. And maybe I shouldn't call this input. Let's call it, what could we call this? Let's call this in tensor. Now, we're used to naming methods, whatever we would like. And we could still do that within this class, right? Because this is still just Python code. But know that the nn.Module is specifically looking for an init method and a forward method. If you do not have a forward method, this will fail because it needs to have a way to pass data from the very start to the very end. Well, let's go through this process of passing our data, right? So let's say linear 1 result is equal to self dot linear 1 and taking in the in tensor. Then we say linear 2 result, and this is going to take in linear 2's, but what it's going to accept is going to be the return of linear 1. And then finally, we can say activation. Let's just do outcome. Yeah, let's do outcome. And here we say self dot activation. And my activation layer would just take linear 2's result. And then finally, my forward pass would return the outcome. All right, so just like before, I am going to feed my tensor data. I pass in the input tensor, or my in tensor is going through my first layer. And here we can see that my first layer is 3 and 2. I am going to grab that output of 2 tensors and feed it to linear 2, which is of 2 tensors. Go through it and do 2 and 1. And then finally, I'm going to feed that 1 output into my activation layer and return the outcome. And that's how I specify my forward pass. Right? So now if I were to do model is equal to binary model. And I could use this the same way. I can go ahead and print model and call the input tensor that we had built before. When I click on play, we'll see that it takes the input tensor, applies the forward pass, and makes a prediction. All right. Does anyone have any questions about how we turned this sequential model into a class learning model? No questions at all. Let's hear it, Ruben.
So is the point of making the class or the learning module to adjust anything that's inaccurate? Would you be doing that inside of the init function?
Could you ask that question one more time? I apologize.
Is the purpose of creating a learning module to adjust any inaccuracy inside of your layer?
Yeah, so the purpose of creating this class rather than having a sequential, as we'll see later on, we're going to have a little bit more dynamic models where we'll have to account for a functionality such as skipping within the forward pass. Sequential does not have a skipping functionality. It's strictly just going to feed from one layer to the next and then return an output. Well, sometimes we'll need to build some extra functionality to happen within these layers. And that's why we need to have it as a class utilizing nn.Module rather than sequential. Does that answer your question, Raven?
It does, thank you.
Brandon?
So just to restate from my understanding, using sequential is like a baseline and a lot of assumptions are made, whereas creating a class allows us to have more control over our iteration process.
Correct. Yes. All right. Okay, great. If there aren't any other questions, I'm going to go ahead and stop the recording here. Let me go ahead and